welcome Dr. Bruce Betts.
Hi there, everyone, and welcome. We've got a great lineup to talk tech on Mars, and specifically Mars 2020 lander, Rover. And we've got talks about the Mars helicopter, and then also two of the principal investigators of the key wonderfully technological instruments that are on the Perseverance rover. So it's going to be good stuff. I will do just short introductions of each of the presenters. You can find longer bios on the Whova site, and we will take, you can ask your questions in Whova along the way, but we will actually take them and answer them at the end of the session. And let's go ahead and get started with Håvard Grip, whose name I've mispronounced undoubtedly. And he is a robotics technologist at NASA JPL. He is also the flight control and aerodynamics lead for the Mars helicopter, and seems to at least unofficially be phrased as the chief pilot of the Mars helicopter. Pretty cool title. I turn it over to you, Håvard.
Thank you very much. Let me share my presentation. Okay, is that showing up properly?
Yes.
All right. So yes, thank you very much. I'm excited to be here to talk to you about the Mars helicopter. As I just said, my name is Håvard Grip, and I'm the chief pilot of the helicopter. And I'll be giving you a short overview, a little bit of a taste of what the Mars helicopter is, why we're sending it to Mars, and what we hope to do with it once we get there. So to get straight to the point, Mars helicopter is a technology demonstration on the Mars 2020 mission. We are traveling to Mars underneath the belly of the Perseverance rover. Once we land on the surface, we will look for a suitable place for the helicopter to be dropped off. Once that's done, the rover will drive off to a safe distance, and we will proceed to perform a series of experimental test flights with Ingenuity for the purpose of proving or demonstrating this technology, the technology of flying a helicopter on Mars. Why are we doing this? Because we think that having helicopters on Mars has a potential to open up a new dimension in Mars exploration, namely the aerial dimension. Just imagine being able to fly around on Mars. Just as we have aerial platforms here on Earth that we use for purposes where they're more suitable than land vehicles, in the same way, we will have a similar capability on Mars. Whether it is for reconnaissance, for scouting out potential routes or science targets for future rovers or future astronauts, or for going places where it is difficult to get with a land vehicle. That is the kind of promise that we believe that this technology has. We will perform up to 5 test flights on Mars. They will originate from an area that we've picked with the rover. We call it the airfield, or the takeoff/landing area, as you see in this slide. And that indicates that we don't not only intend to take off from there, but we intend to fly around and then come back and land in that area again. That being said, if conditions are suitable for going and landing somewhere else, we may choose to do that towards the end of this up to 5 flight mission. We'd like to draw some parallels between this mission and what the Wright brothers did in their day. Because what they did is they demonstrated that it's feasible to perform powered, sustained, controlled flight in Earth's atmosphere. You could say that they performed a technology demonstration with a purpose-built vehicle. And that is exactly what we're trying to do with Ingenuity, except of course that the point is to fly not in Earth's atmosphere, but in the atmosphere of another planet. I'd like to show you next a short video that illustrates some of the things that I was just talking about. So that was the computerized version of Ingenuity. And what you see here is the real thing. This is Ingenuity photographed shortly before it was packaged up and sent on its way to Mars. And what you see here is what we call a coaxial helicopter. It means it has two rotors, one on top of the other, and they spin in opposite directions. The rotors are about 1.2 meters tip to tip, and they spin at about 2,400 RPMs during flight. Now, we don't control the helicopter using the RPM. Instead, we control it by changing the angle at which the blades bite the air, so the so-called pitch angle of the blades. Now, if you had a rotor spanning 1.2 meters diameter and you spun it at 2,400 RPM on Earth, you could lift a lot of weight with that. But as you can see, the Mars helicopter is only 1.8 kilograms, or about 4 pounds. And the reason for that is, of course, this being Mars, there are some challenges. And one of the big ones is the density. The density of the atmosphere on Mars is only about 1% of the density of Earth's atmosphere at sea level. That's equivalent to an altitude of about 100,000 feet above sea level. What that means is we can simply just not produce as much thrust. We can produce a lot less thrust with the same type of rotor. Now we get some help from gravity, which is about 38% of the gravity on Earth, but it's still not enough to make up the difference because of the low density. Now, there are some other challenges about flying on Mars. There's a long distance, of course, from Earth, which makes communication take time and it's more difficult. And it's also very cold there. It can get down to about -90 at night. So not only did we have to build a helicopter that's light enough, small enough that it can lift itself in the thin atmosphere of Mars, but it also has to have all the features necessary to survive and operate on Mars. That includes having a battery to power itself, a solar panel to recharge that battery. It includes being able to control its own temperature to keep itself warm. It includes being able to communicate with Earth via the rover. And of course, it includes having all the sensors and actuators and the software on board to be able to fly itself based only on the instructions that we send to it prior to each flight. It's another schematic of a vehicle that's capable of doing all of those things. In order to be able to do that, we had to make use of very lightweight materials, a lot of carbon fiber in the landing gear and the blades in particular. You can see that it has a solar panel above the rotors on a non-rotating mast and a telecom antenna on top of the solar panel again. Below the rotor, there's a cube, which is a thermal enclosure where you will find the batteries and the avionics and various sensors necessary for performing the flight control. Now, of course, this is the end product, if you will, but this started out, 7, 8 years ago, just as an idea or a concept of flying a helicopter on Mars. And so I want to spend next few minutes talking a little bit about the path from that initial concept to actually being able to send a helicopter to Mars. And it started out with the sort of fundamental first question. Can you really lift a helicopter in the thin Martian atmosphere? Because the first thing you think about when flying a helicopter on Mars is the atmosphere. Is it possible? And so we had to answer that question. And to do that, we performed an experiment. This was a tiny, lightweight vehicle with a fast rotor that we built, and we put it inside the JPL 25-foot space simulator, which is a big vacuum chamber where we can replicate the Martian atmosphere. And we controlled this vehicle with a joystick from the outside. And I'll show a short video clip of what that looked like. As you can see, it did indeed create lift. It came off the ground, but you can't really call this flying. because, it's more like uncontrolled hopping around. So besides showing us that, yeah, okay, our predictions regarding lift were good enough, it also showed us that there's a lot more to this problem than just generating lift. In particular, we really had to focus on stability and control of the helicopter in the Martian atmosphere. And we learned that there are some big differences, clearly, between controlling it on Earth versus on Mars. So that led us to the next phase of this project, which was centered around another question. Can you fly a helicopter in a controlled manner in the Martian atmosphere? And that in many ways turned out to be a much more complex question to answer, because now we had to really delve deep in understanding the flight dynamics on Mars and how it differed from Earth. And it turned out that there are some really significant differences, and they affected not only the algorithms that we use to fly it, but also the physical design of the vehicle itself. It culminated in building this vehicle, which is a proof of concept helicopter that we built with a full-size rotor system in 2016. Full-size rotor, everything else is basically slimmed down or stripped away just to perform this one task of trying to prove that we could indeed fly it in a controlled manner. And indeed, we did use this helicopter to perform the first controlled helicopter flight in Martian atmospheric conditions in the 25-foot space simulator. And I'll show a short clip of that too. As you can see, this now actually worked. Okay, we've proven, it's possible to fly a helicopter in a controlled way in the Martian atmosphere. So now the next task was, can we cash in on this and actually build a helicopter that not only can do this task, but also have all the bells and whistles to survive the environment in Mars and operate as designed there. So all of those things that was stripped away on this demonstration vehicle that's just basically a mast with a rotor on it, can we add all of that on and have it be robust enough to survive? The effort to do that culminated in building 2 engineering development models, one of which you can see here. And now you can see this is starting to look a lot like the Ingenuity that you saw up front. This is, for all intents and purposes, the same vehicle. And we built 2 of these and we put them through the ringer in terms of testing them for both environmental purposes and for flight dynamics. This is just one example of the kind of testing that we put it through. In this case, we swung it back and forth with the rotor running in order to measure the response to edgewise flow over the rotor. It's sort of poor man's wind tunnel, if you will, in the 25-foot space simulator again. And of course, we performed more flight testing. So having gone through all of those tests with our engineering development models, that was really the final step before we could actually go to work on building Ingenuity, the helicopter that we're going to send to Mars. And you've already seen a picture of that, but I want to show you another picture, which is Ingenuity tucked underneath the belly of Perseverance in the same way that it is right now on its way to Mars. And you may not even see it right away underneath there. But if you look closely, you'll see the blades in the solar panel and the legs folded up underneath the belly. This is another image of the 2 of them together, this time with the helicopter deployed on the ground below Perseverance, similar to what it will be after deployment, but before the rover has driven away on Mars. So Perseverance with Ingenuity attached to it launched last year on July 30th. And in just a few days, we are landing on Mars. And I hope everyone listening here will be following closely what happens next as we try to perform the first helicopter flight on Mars. Thank you.
Great. Thank you so much. That was great. Fascinating. We're going to move on. We'll take questions at the end again, but you can put them into Huba. And next, we'll be going to Dr. Roger Wiens from Los Alamos National Laboratory, the head of the ChemCam instrument currently on Mars with Curiosity, and the SuperCam instrument on Perseverance that he'll be talking to us about, and the man responsible for sending lasers to Mars and vaporizing rocks with them, and doing some really amazing science. So I turn it over to you, Roger.
Thanks, Bruce. Can you hear me okay?
Yes.
And you can see my screen?
Yes.
All right, perfect. And Navard, that was just an awesome explanation of the helicopter. I'm so excited for that too. So SuperCam does come on the heels of ChemCam. And when the science definition team decided what the Perseverance rover was going to do, they decided that the remote sensing on Perseverance would study mineralogy. And I don't know if they thought maybe they got rid of us or what, but ChemCam does chemistry. And so we tried to put our heads together to figure out what are we going to do. Now, I'll tell you in a minute why mineralogy is so important. But first, I want to just show you what ChemCam does, because we built SuperCam basically on the same architecture as ChemCam. And so next, I think I have a short video if this works and if I can advance my slides. Okay. And so first, you'll just see both. This is just a point and focus and shoot instruments. So it's conceptually simple to operate. And so it has two parts. This part sits inside the body of the rover, and it is the sensing part with the spectrometers and detectors. And it gets the light through optical fibers. You see these white things at the top. Those come all the way down from the mast of the rover, which is where this part is. And you should be able to see the laser on the left. And in this telescope, which is 110 millimeters in diameter, it's the largest optic on the surface of Mars. So and it's about to be joined by SuperCams. And so we focus this telescope, which is doing right now in this demonstration, and we're going to shoot at an iron pyrite target about 8 feet away in this demonstration. You don't see the laser beam because it's infrared. You don't see it, but you see the flashes, I hope, in your video from the sparks or the little implosions that we make on the target. And it's optically bright, and that's why we can do this to about 25 feet away, 7 meters away. But when this came up and we were planning to do this on MSL, some of the press got pretty excited. People didn't know what exactly we were going to do with this big laser, and they thought we were going to like blast the whole rock. And so on the internet, you know, we saw a picture that looked kind of like this. And so, of course, we don't do that, but, you know, it is pretty cool using these lasers on Mars. So this is actually what we get scientifically. It is an optical spectrum of the visible and near infrared portion of the light. And actually, I'll just show the little rainbow of colors down below it. And so you can see that we go down into the ultraviolet quite a ways, and then a little bit into the near infrared, and then the optical colors that you can see there as well. And so we actually match this same spectral range with SuperCam. And it's the position as a wavelength of these emission lines that we get in that spark, in that light that you get that tell us what elements are there. And I've got them labeled on this, on this plot. And then by calibrating them, we can tell what is the composition of these rocks or soil up to 25 feet away. And not only that, but the laser does make a little implosion, and it blasts the dust away. And so the rocks that we shoot are pretty much cleared of dust, which really helps us a lot. There's no other remote sensing technique that does that for us. And so why is mineralogy so important for Perseverance? So right in the middle of the screen, you have 3 elements: calcium, carbon, and oxygen. And so that is important to know for the chemistry. And so we've actually published 102 papers on the results of ChemCam. But speaking of minerals, calcium carbonate can make at least two different minerals that are somewhat common, and in others as well. So on the left, you have calcite. Calcite is a major constituent of limestone, which is a major sedimentary rock on the Earth. And it is produced inorganically at relatively low pressure, so precipitating calcite from water, from lakes or the ocean. And so that's how it is produced. But on the right-hand side of your screen, you have aragonite, and that's very different. It's either produced by biological processes or at high pressure. Now, you can understand why that could be very interesting for Perseverance, because if we were to see aragonite and it was to indicate that there was some past form of life on Mars, that could be very, very important. So that's why not just the chemistry, but the mineralogy is very important for us to study. And so SuperCam can obtain both chemistry and the structure, which is the mineralogy. And you're going to hear about mineralogy from Luther Beagle as well in the next talk, because we're actually both using remote Raman spectroscopy to do, or we're using Raman spectroscopy. SuperCam is using it in the remote sense that we shoot at rocks and soils several meters away or many feet away. And then the arm of the rover has the Sherlock instrument that Luther will tell you about in a little bit. Now, I hope you can see this video. This was taken in about 2015, and we were basically, we had a prototype spectrometer for this, but we didn't have the electronics built up yet. And so you can see all of these different power supplies that are powering the parts of this spectrometer that we had to get to do this Raman spectroscopy. There's a laser. You'll see the telescope in just a minute, and we're projecting this green laser light, in this case, way out to 8 to 12 meters away. You can see this on the rock. Now, we don't blast these rocks, so there's no ablation, no pits made, but we tickle the surface, and that basically excites the molecules, and they vibrate, and we get these signals back about the bond strengths that it basically tells us what the molecules are. And the workhorse behind this, besides the laser, is this little spectrometer right here. And so we took ChemCam and we substituted out one of ChemCam spectrometer for this thing, which is really quite complicated. But looking at the middle of this, at the very center, you'll see this image intensifier here. And that's the key to this, because from a few meters away, Raman spectroscopy is a very kind of faint technique. And to get enough photons, we had to use this intensifier, and we got this out of basically off of a military assembly line for night vision goggles. And we made it to work in the thin air of Mars, which is a fairly tough thing to do because there's lots of high voltage in this. And so it collects the few Raman photons that are coming to SuperCam from meters away, and it cuts out the daylight, and it separates fluorescence from Raman signals. And that's all needed so that we can get the Raman signals a few meters away. And so we get, oh, and I have a little side story here I just want to tell you. We had this part all pretty much developed by 2017, at least this part of it in red. And so we took this off, and we actually did a spin-off of a new technology development. And we made a really tiny instrument, much smaller than SuperCam. And we want to target that using like a helicopter from Harvard's group, and I've talked with some of their team members, and potentially go through skylight caves into the underground of Mars. So we actually won an R&D 100 award with this OrganiCam instrument prototype that we did. So anyway, think about that for the future. But back to SuperCam, this is the signal we get from the Raman spectra of the minerals. And so there's a number of different minerals represented by all the different lines you see there. And so they're labeled a little bit right of center. And what they're doing is the position of those peaks is telling you about the bond strength. And that bond strength is sort of represented over here by all these molecules that are vibrating. But Raman doesn't get all of the minerals, and so we have yet one more technique on SuperCam. That's why it's super, it has all these techniques. And so some of the bond vibrations, the types of vibrations that Raman doesn't get, our infrared spectrometer gets. And so our French colleagues, which we're partnering with in both ChemCam and SuperCam, they developed this little tiny infrared spectrometer that looks at 1.3 to 2.6 microns, and we're just looking at reflected sunlight, but this takes that light, it sends it through a crystal which is shown in red in the middle, and we vibrate or we modulate that crystal with radio frequency, and it actually bends the light of certain wavelengths, and we can detect them and get a spectrum, color spectrum in the infrared, which tells us more about the mineral content of the rocks and soils that we're looking at. Now, beyond that, we actually added something that wasn't originally in our proposal, which is a microphone. And this is one of two microphones on the rover. The other one is going to be listening to the descent and entry of the rover. But ours is really intended to do science. We will be listening to the zapping sound that the laser makes when it shoots a rock. And it turns out that if that laser is actually profiling deeply into the rock, by deeply I mean a few hundred microns, then the sound changes. And so that's shown in this slide right here. On the upper plot here, if the sound is changing a lot over a few shots, like 150 laser shots, then it tells us that the rock is rather soft. If the sound doesn't change much, like these top plots on the right, then it's quite hard. And so those are plotted. The difference between the beginning and end are plotted in the lower plot, and that tells us the hardness of the rock. And it could also identify coatings that might be on the surface of the rock, and so on. So we think that's going to be really useful. Then the microphone can also help us determine the wind speed and the direction, and be used for turbulence studies. So we think that's going to be really useful as a scientific instrument beyond just the gee whiz, how do things sound on Mars. Then we have one of the highest resolution imagers through SuperCam. That's why it's called CAM after all. And so this is looking using the images in color. So these are high resolution. We're looking at very small spots. You can see the laser pit right there on the right that's blown up, and that's just a fraction of a millimeter. And remember, we're looking at head height down or off to the side at rocks and soils. So very high resolution imaging that we can use to study what we're actually looking at. Okay, now we'll do these studies using rasters. The LIBS chemistry technique actually makes these laser pits. We can shoot at all kinds of different minerals within the rocks, as you can see in the lower left. We can shoot down the drill hole as well. And so all of these ways we will be analyzing the surface of Mars with SuperCam. And so just kind of in summary, SuperCam, I like to think of it as a geological observatory, all right? It's got this telescope, and it's providing us chemistry, mineralogy in two different ways, organics through those, rock texture, and physical properties in a single package. I don't know if you can hear this, but I think I have a recording here. So just in closing.
You are hearing this voice through the SuperCam Mars microphone.
And so it's going to be pretty cool. And so that is SuperCam. This is the last picture of getting installed on top of the rover. So thank you for your attention.
Thank you, Roger. I never cease to be amazed by how many things you've got going on in what's ostensibly one instrument. You have an amazing number of things. I will note that Nina Lanza from your group at Los Alamos spoke earlier today in one of our sessions about the microphone specifically. So if people want to learn more about that, check the archive of that session.
Absolutely. Thanks for mentioning that.
All right, we move on to Luther Beagle. Dr. Luther Beagle is at JPL, and he is the principal investigator of the Sherlock instrument, which is on the, well, I'll let him tell you about it. He's also the deputy manager for the science division there at JPL, and really glad to have you here, Luther. I turn it over to you.
Thanks, Bruce. Really glad to be here. Glad to talk to everybody. I hope you all can hear me. I'm going to pull up my slides here. Can you see my slides okay?
We see it, but not in presentation mode, but yes.
All right, let me try that then. Okay, hopefully this is in presentation mode. And I'm going to talk about Sherlock, basically what we're doing on the end of the arm, looking for clues in Jezero Crater. And these clues can be about the habitability and the history of Mars, history of Jezero Crater, and looking for something we like to call potential biosignatures and biosignatures as well within Jezero Crater to help sample return, which will be talked about, I think, in a tomorrow session. So this is the Mars rover. I think Roger showed a picture of this earlier today, and we are here on the end of the arm. Now, I like this picture a lot. We've been working on Sherlock for the better part of 20 years. But this is a picture I like of the Mars rover even better because it's got Sherlock out in front in all its glory. And this was the last image we took of the instrument at ATLO right before they put in the drill at JPL. And this is the way I actually look at things with Sherlock leading everything. But that's just me. This is the 7 instruments plus the helicopter that we already talked about that are on the Mars rover. There are 23 individual cameras on this rover, plus 2 cameras on the helicopter, which is, I think, the most heavily cameraed mission that's ever flown. We actually have 3 of them.
Luther, I'm going to interrupt you for just a second. We don't,
Yes.
At least I'm not seeing past your first slide, and at least some other people are experiencing that as well.
Oh. Let me get out of presentation mode. Is this better?
And I never saw it go to presentation mode. Yes, now that works. We see the slides moving, so sure.
Okay. Well, so I'll get back to where I was. So this is Sherlock on the rover. This is what I was talking about earlier. This is the last picture we took of the instrument here as it was on the end of the rover arm right before they installed the drill and shipped to the Cape. This is the rover itself. There are, like I said, 7 particular instruments on here. Roger's already talked about SuperCam, 23 individual cameras on the rover itself, 2 cameras on the Mars helicopter, making 25 altogether. And the reason I bring that up is that we have 3 cameras basically inside Sherlock. And I'll talk about why we have 3 inside such a small volume in a second. The challenge of actually doing Sherlock was a bunch of different challenges, but this is a new technology that's never been flown before. And one of the things that you have to worry about on Mars is this survivability of temperatures. On the end of the arm, we're exposed to all of the atmospheric temperature ranges. It can go down to minus 100, minus 110 degrees C. During cruise, we can be up to upwards of plus 40 degrees C. And every single day, the temperature on Mars changes about 80 degrees Celsius per day. So in the morning, it's very cold, moving up to about 0 degrees C at the middle of the day. And all of our 26 optics have to stay aligned within a handful of microns over this temperature range. And for those people who know what happens when you change temperatures, things contract and expand depending on how hot things are. And this really does make for an engineering challenge. The other thing is that we're in a very small box. Sherlock itself is in a box about the size of a shoebox. And there's a lot of things in there that really want to be hot, and there's a lot of things in there that really want to be cold. And the thing of it is, the hot stuff is right next to the cold stuff, and the cold stuff is right next to the hot stuff. And that's really difficult to engineer out. So we had to put a lot of thought and processes into making sure that worked. Like I said, we have 3 CC detectors integrated into 1 spectrometer and 2 different imagers that had 2 different bore sites associated with it, and I'll explain what that means in a second. We also operate, as surprising as it is, we're about 100 million kilometers away. We operate on a 1.5 meter, 90 kilogram, which is almost 200-pound robotic arm. We need to know where we are within about 100 microns of the surface. And incredibly, that robotic arm gets us to within a few handful of millimeters on the surface, so we know where we are. However, we still need to focus a little bit more on the surface, and we also need to be able to move our laser around within about 100 micron steps. And 100 micron steps are about the size of a human hair. So we're looking at things very, very small spatial scales, 100 micron spatial scales. And so this puts a really a difficulty in understanding context, because you want to know exactly what you're looking at in order to come to scientific conclusions. So Sherlock, I said, is a spectrometer and 2 imagers. We have an instrument team at JPL that consisted of more than 30 engineers. 100 people total contributed to this, much more than 100 people, and a lot of different major partners out there. And as Roger pointed out, we do Raman. We do Raman like SuperCam does Raman. We do it on a little different scale with a little different lasers, so there are some subtle differences. We look at fluorescence spectroscopy for organic material, and we make maps. So we take our little 100 micron laser point, and we shoot down, we look at the spectra that comes up, and we scan across the surface. And we take all of those individual spectra and we overlay it on a picture we've taken, and we can come up with really cool microscopic maps, and I'll explain what that means in a second. This is the science team, which looks better when it's in presentation mode. These are the engineers that helped us deliver it. This is actually, we're delivering it, we've put it in the crate, and our science team's in the background. They're not going to get any credit right now. Anyway, there's 3 different Sherlock assemblies. One is at the end of the arm. This is the end of the arm, the Sherlock turret assembly. We have a Sherlock body assembly, which was within the warm box of the rover. And the reason is I talked about the temperature swings on the end of the arm, every single sol. The electronics don't like going through that. So in order to be able to survive a Martian year, we put ourselves inside the warm box so that the electronics stay cool. And we have a really cool Sherlock calibration target at the front end to make sure our instrument's working. So what is Sherlock? Well, Sherlock stands for Scanning Habitable Environments. What we're doing is looking for places that could have been alive with 2 different spectroscopy techniques. As Jim Bell pointed out earlier, these are squiggly lines that scientists love to look at, with Raman spectral lines and fluorescence or luminescence spectral lines that looks at organics, for organic material and chemicals. We look for organic as in terms of aliphatics, which are basically amino acids, proteins, and things like that, and aromatics, which are polyaromatic hydrocarbons. Think of them as soot. And astrobiology relevant minerals. We can do mineralogy detection and chemical detection as well. Plus, we have, as Sherlock had in the books, we've got Watson, which has a couple of different acronyms. Right now, this was the first acronym we came up when we thought we were going to add Watson on there, which is the Weird Appendage Act, the Sherlock for Operations and Navigation. The actual acronym for it is Wide Angle Telegraphic Sensor for Operations and Navigation. But we just liked that it had 2 different acronyms because we like to do acronyms at JPL. With Watson, we can do the rover selfies. We can look at how the rover is doing engineering wise, and we'll be able to take images of the helicopter actually deploying in the first 60 days of the mission. So when the helicopter drops from the rover pan, we'll be able to take images of that. Plus, we take microscopic images and contextual images for both us and Pixel and SuperCam, which we'll talk about here in a second. These are just more images of all the things we can do. So why are we doing Sherlock? Well, we do Sherlock for several reasons. One, it involves very simple sample handling on the rover. We just want to brush off the dust from the surface, but we can see things that normally you wouldn't be able to see with just the naked eye. This is a deep sea carbonate from underneath the ocean surface. And as we scan through this using the laser, we can scan over it. We can see where there's organic material and when there's no organic material. Now, for those of you who have seen what a stromatolite is, this basically is a stromatolite in formation. It just does not look like a traditional stromatolite, but it actually is, because the organic material is here, organisms are growing, and then they go through a little piece where there's just abiotic chemistry going on, then there's more organics, and there's more organics, and there's more organics. And what we can do after we do the laser and the fluorescence, we can zoom in on one particular spot and take a really nice image and get a Raman image and say that, wow, we've made carbonate, as Roger pointed out, calcite. This is a calcite carbonate, and we can tell a lot about a sample, both from the imaging and from the spectroscopy, more so than you can do from either one, either technique. what we can also do is we can scan for hidden textures. This is a stromatolitic rock as well. And what we did was, this is one of the first things we had looked at. We're really interested in finding out where on this particular rock there are organisms that could potentially live. You can see in here in this rock that there are crevices and cracks, and there's an outer region here. So what we did is we cleaned off the rock. We made sure there was no organic carbon on the rock, and we were just looking for where bugs are. And you can see our scan down here. And so what it did is the individual laser comes by, shoots a laser point out at an individual spot, and if there's a lot of organic material, it says there's a lot of organic material here. So in this image down here, the dark purple is where there's a lot of organic material. And so you can see here, we can see where there's a lot of organisms on the outside of the rock. You can see where there's a lot of organisms living in the cracks of the rock. And what was really confusing about this particular rock is this feature here and this feature here. We couldn't figure out what they were at first. And the more we looked at it, the more interesting it was, because microorganisms shouldn't be able to live in these particular portions of this particular rock, and there doesn't appear to be anything contextually there. And then we realized after a while this was a fingerprint. One of the postdocs had picked up the rock after we had cleaned it off and put a fingerprint on it, and you can see where the lines are here. That really does show how sensitive we are to organic material. But the rock actually looks exactly like we thought it would, except for the two fingerprints, and that postdoc has been embarrassed every single time we show this, which is why we like to show it. Last thing I want to talk about is a calibration target. If we find anything cool on the surface, we want to make sure that what we're seeing actually exists. So we have a series of calibration targets that we know exactly what it should look like on Mars. So what we'll do is, if we see something really cool, we will look at the calibration target, make sure the instrument's working properly. But we also have a few experiments on here. These 4 samples down here are Spacesuit Materials. They're the one. This particular instrument, this particular part of the instrument was created at Johnson Space Center. You can see, we're going to see how the spacesuit material operates over the course of a Martian year. These are materials that go in gloves and visors and the like. And we also have a piece of Mars that we're sending back, which we can actually map out, and we can see whether there's any changes in it. And that's all I have, except to thank everybody who helped us build this and put this together. So thanks for listening, everyone.
Thank you, Luther. That's another amazing instrument. So will you be able to detect fingerprints on Martian rocks? I'll just assume that's a yes. But we probably don't expect to find them. So I'm going to go through some of the questions and direct them to our speakers, focusing on ones that they have that's tied to the expertise of our panel. We've gotten a lot of great questions over a broad range of things. We'll start with Håvard, and then I'll go to Roger. What altitude is Ingenuity expected to reach in flight? And also, how far away from the rover is it expected to fly?
The first flight, we're going to go 3 meters to 3 meter altitude, and subsequent flights we expect to fly at about 5 meters. And we maintain a distance from the rover of at least 100 meters at all times.
So you're at least 100 meters, but you could be significantly more?
Yes, absolutely.
Got it. Okay, Roger, tied to something I didn't expect you to bring up in your talk, the pits, the tube subsurface things. We had a question: what engineering challenges would we have to overcome to explore Martian lava tubes and pits, which could likely be future human habitats or sources of samples unprotected from the intense surface radiation? Thoughts?
Well, yeah, there's a huge amount of challenges with that. First of all, these are vertical drops of up to 150 or 200 meters. Those were vertical holes into a lava tube cave. That's why I think, that's why I'm bullish on Mars helicopters, by the way. I think that's the way that will be the very first exploration of the underground on Mars. And so I think, what my aim is to try to figure out what kind of tiny instrumentation we could use to figure out if there are organic materials that could suggest biosignatures in those caves. But the challenges are huge, and I'm sure Håvard knows more about that. But once you get over the opening of a cave like that, there's going to be a lot of turbulence, because the caves, I don't know if you know much about caves and their physical properties, but they breathe. there's a wind that goes in and out as the atmospheric pressure equilibrates. And so doing anything going in or out of that hole could be very challenging aerodynamically speaking. So that's one thing. And the other thing is to actually scale up a helicopter to a size that could carry a scientific payload. So that's, I'm sure, something that our folks at JPL are going to be thinking a lot about once they have success with Ingenuity. So anyway, I just thought it was worth mentioning in this talk, because that's the future, I think.
Fun and interesting. All right, Luther, got one for you. How did you insulate the hot/cold components on Sherlock?
We have a lot of standoff ceramics that make sure that the heat does not flow from one side to the other. Plus, we went through the design of at least 4 different designs to make sure it would work.
All right, thanks. Hovard, if you're willing to speculate, if Ingenuity succeeds, what's next? A bigger helicopter, longer missions?
Yeah, I don't want to speculate too much, but what I can say is we're looking, at what the possibilities, are for helicopters that can carry larger payloads and that have, longer range and endurance. And so what we're thinking of then is, on the order of, 10, 15 kilogram vehicles that can carry science payloads on the order of, a couple of pounds.
Great. To Roger, from Alex, 11-year-old watching, what would happen if the laser were to hit a human? Breaks rocks, apparently makes my dogs bark. What do you?
Yeah, hi, Alex. So these lasers, like I showed already, they don't really blast a whole rock, but they will make a small pit in things. And so if somebody were to stand in the way, their skin would get a little bit of a burn mark on it. So please don't ever do that. We're instructed to never walk in front of a laser here at the National Laboratory, Los Alamos. So don't ever experiment with that kind of thing. It wouldn't kill you, but it's just not good for your skin.
Important safety tip: do not try this at home. Hovard, is it possible for the helicopter? Is it possible for the helicopter to operate even if degraded in the event of one of the propellers failing?
No, it has to have both of the rotors in order to function. As you can picture that, with just one rotor, the body below it would spin in the opposite direction if you tried to spin that rotor. So the 2 rotors counteract each other to cancel the torque on the body itself in the same way that the tail rotor does on a classical helicopter.
Got it. And back to you again. a lot of helicopter questions, not surprisingly. How does such a light craft stay safe from windstorms?
So one of the nice things about there being, the density being as low as it is that you become less susceptible to wind. So if you're just sitting on the ground, the same wind speed as on Earth, would not, generate the force on you that's comparable to what you would see on Earth. That's why we have to spin the rotors as fast as we do. We spin them at 0.6, 0.7 Mach at the tips in order to generate enough thrust just to lift that mass off the ground. And so that same, low density makes us more robust to wind when we are sitting on the ground. And I should add, if there is a storm, we don't go flying at the same time. We do watch the weather, and just as we would in flying on Earth.
Another question, I'm not sure if it's Luther or Roger, so I'll let either of you jump in. So if you find, say, magnetite and carbon in the same rock, you'll know if they were close together or not.
I'll take that, and Roger can jump in after that. Yeah, we would find them next to each other. So that's one of the reasons why mapping is so important. We scan that laser through the rock. We'll be able to see the magnetite and we'll be able to look over 150, 200 microns to find out whether there's carbonate next to it. Instead of just understanding whether or not the bulk properties of the rock, we're actually looking at it at 100 micron scale, which is really adds to the scientific feedback of what you're going to get.
Yeah, and I'll just add that.
Go for it.
Sherlock is the instrument to answer that question. They're the ones that have the good spatial resolution. So yeah, that's exactly what Sherlock is made to do.
But let me focus in on that a little bit more, because we all take images, because the SuperCam does, Pixel does, and Sherlock does. We actually start taking this multiple different measurements with different techniques on the same spot, and that really does increase the scientific output of everything. Because I can look at where Roger's 2 millimeter spot is and look at it in a much smaller spatial scale. I can take my map and overlay it with Abby's map and Pixel's map, and then we get a really good understanding of the science of the entire thing. So it's very powerful.
For Howard, first of all, a comment. Apparently, you have the best job title in human history. Congratulations. Question is, how robust is the chopper? Can it handle hard landings?
So we have designed it so that it can handle, harder landings than what we're actually going to do with it. We have an envelope that's fairly generous relative to what we're touched down with. Now, I should say the way that we do touch down is not by trying to really softly place it on the ground. Rather, we fly at the ground at 1 meter per second. And then once we detect that we've touched the ground, then we just cut the lift. And so we don't spend time trying to really softly put it down.
All right, back to you. Any concerns about dust with the helicopter?
So dust is a difficult thing to predict, exactly how it's going to behave. And so we do assume that we could have some amount of dust kicked up by the rotors. And so in order to not have to predict every detail of that, we've designed it so that we just don't use the sensors that would be susceptible to dust when we are close to the ground. So that includes the camera and it includes the laser altimeters that we have on board. We only use them once we get above where dust would be a problem.
Got it. And one more, sorry. Will the flight of the helicopter be filmed by Perseverance?
We expect to get pictures, of the helicopter from Perseverance. Not full frame rate video or anything, but pictures.
Great. We only have less than 2 minutes left, 1 minute left. So I'm going to go ahead and tie it off with questions and thank our panelists. You're all great. I really appreciate you being here. I appreciate my dogs being involved through much of the presentation. So thanks to Max and Gracie, and everyone enjoy Planet Fest and take care.
Thank you all.
Thank you.
Thank you all so much to our speakers today as well for sharing their expertise with us. Just so you know, Beyond the Horizon begins in just a few minutes. I guess not a few minutes, in about 30 minutes. Tune in at 5:30 p.m. Pacific time, and please invite your friends and loved ones. It is free and open to everyone who loves space. Thank you all so much, and thank you to our speakers today. Have a great day. What a great day one of Planet Fest. Bye, everyone.